All right, this is the 13.3 video. This is your first section on partial derivatives. So partial derivatives are the derivatives that you would take when you have a function of more than one variable. So like f of xy, f of xyz, something like that would be something that would need partial derivatives. And so as usual, I'm not going to read to you out loud. You can either pause the video and read this stuff as you go, or you can wait and read it at the end. But you definitely want to read this information on page 703. It has a lot of information. I'm basically just going to go through and tell you kind of in my own words what's going on here, but this would be a much more thorough and math-specific, I guess, explanation of what's going on. So definitely read these things that I show you always. But what we're going to look at is a pictorial representation first of what we're doing. So on page 704 and 705, they have these two pictures, which would be the individual cases as separate pictures, but I'm going to look at this where they put them both together. So if this is too much going on in one picture, you can look here and here for the two separate cases. But here's what's happening graphically, so you can kind of get an understanding of what we're doing. What you have here is the graph of some function z equals f of xy. So if it's z equals f of xy, the graph is in 3 dimensions. It's a surface, and that would be this green thing, this surface. Then what you can do is you can take the plane. So here they have a plane y equals y naught. So y naught's a number. So let's say it's y equals 1. If you take the plane y equals 1, that would be a plane, you know, like this, and intersect that plane, that surface with the plane, then the intersection of the plane, which is, you know, up and down like this, and the surface is this blue curve. Okay, and so on this blue curve, because you have y equals a constant here, then your y's are now numbers, and so it's just a function of x. And so when you take this derivative, it would just be a function of x. So when you do the derivative, what you're finding is the slope of this tangent line here, and so that would be a picture representation of what's going on when you take the derivative with respect to x. And then similarly here, let's say x is also 1. X equals x naught's a number. So that would be a plane that goes this way. And if you are intersecting the green surface with that plane, you would get, where's my finger there? This blue curve here. And then you can do the tangent line, that's this one here, the tangent line to that curve, and the slope of that tangent line is the same thing as the derivative, but that would be, because x is a number, that would be a function of y, so that's going to be the partial derivative with respect to y. So kind of the idea on what's going on with this, on partial derivatives, is they're taking turns, and so when it's when you're taking the derivative with respect to x, you're treating y's like numbers, and you're treating x's like variables. And then when you take the derivative with respect to y, you're treating y like a variable, and x's like numbers. And so that's kind of what's going on pictorially. And you can again, look at the separate pictures up here if that's easier. But let's look at some notation now. This is notation for partial derivatives. So remember, f of xy is the same thing as z, so they kind of use f and z interchangeably here. So these would be kind of the basic for f sub x. This curly, I call it curly d. It's, I think delta. I think it's the lowercase delta, but I wouldn't quote me on that because I'm not proficient in my Greek. But it's a Greek letter, but it's the lowercase version of it. Anyway, I call them curly d's. So curly d's and straight d's are not the same thing. This straight d would be like a regular derivative. This curly d would be a partial derivative. So when you see a straight d, it means regular derivative. Curly d means partial derivative. So this is the partial derivative of the function f, which is the function of x and y, and you're taking the derivative with respect to x. Or you can say z sub x, or you can say dz dx. Probably the first one and the last one are probably the two most common that you're going to see. Those are the ones that I mostly use, but any of them are fine. And then these down here are just if you're plugging in a point, like you want to find the partial derivative at the point 1, 2 or something. So the x naught, y naught, they're it's an order pair, they're numbers, and so you could put the order pair in the following places, and that would show you that you're taking the derivative, kind of like in Calais. Like you would have written it like this, and that would say take the derivative of f and then plug in 2. This is the Cal-C equivalent of that. You're taking the derivative of f with respect to x, and you're plugging in the points. That's kind of what's going on there. All right, the top of page 705, they have the notations for the partial with respect to y. They don't have the z's here for some reason. I'm not sure why. You can use the z's here as well. So everywhere you see F, you can substitute in a Z, and that would work also. Okay, so a lot of reading there, but basically what it boils down to is you're taking turns on the derivatives, and when you're taking the derivative with respect to x, you treat y like a number. When you take the derivative with respect to y, you treat x like a number. And here they say constant. That's basically what they're telling you here above example 1. They say constant, but number, same thing. Okay, and then they talk here above example 4 about implicit differentiation. And so we'll look at that with an example. Here it's talking about what to do if you have more than just xy. So like if you have xyz, that's on page 70, what page was that? 707. And then here they talk about partial derivatives and continuity, which we talked about before with continuity, so you can look at that. That's above example 8. And then now for second partial derivatives, in Calais, second derivatives you just wrote, double prime, right? But here hold on, did I have one? No, let me show you. So here's basically what happens. You start with f of xy, and then for your first derivative, you can take the derivative with respect to x, or you can take the derivative with respect to y. And then for your second derivative, for this one, you can do it again with respect to x, or you can do it this time with respect to y. And then here, you can do it again with respect to y, or you can do it now with respect to x. And so notice so this is first derivatives. There's two first derivatives. But then on second derivatives, there's 4. Okay, so 2 first derivatives, but 4 second derivatives. And so here's some notations for them. Notice some of these are a little bit tricky, and I'm going to show you a way you can... oh, no, it's on the next page. I'll show you on the next page. Anyway, this is the bottom of page 708. So here's the subscript one, see there. But then notice here, and I'll show you on the next page, see how they're backwards? See how here it's yx, but here it's xy? That's not a mistake. Okay, see how here it's xy and here it's yx? Also not a mistake. So if you look at the top of page 709, if you look at it with the parentheses, then it makes more sense. So here, what you're doing is, if you do it in terms of one piece at a time, first you're taking the derivative of f with respect to y. Then you're taking the derivative of that answer with respect to x. So it's actually this one first, and then this one. So it makes more sense if you write it in the parentheses like this. But if you look at it, well, here, if you look at it here, see how it seems backwards. But that would first be y, then be x. And so then this is the same thing. The parentheses here don't really help. So I wrote a little note here. In general, these are actually the same thing, but not always. So usually these two end up being the same thing, but not always. So down here it tells you when they will be and when they won't be. Clairaut's theorem is... this is just the name of the guy that came up with this. So this is the bottom of page 709. You can look at this, and it's saying if it's defined throughout an open region and they're both and they're continuous, then they'll be the same thing. So for your purposes, for what you're going to see in your homework problems, they are pretty much always going to, well, I think they're always going to be equal to each other. But just be aware that there are some situations where they're not necessarily going to be the same. So anyway, that's just kind of FYI. Okay, and then lastly, a couple more corollary theorem definition-y kind of things on page 711 that you can look at. It has to do with continuity and differentiability and their connection. So, all right, let's look at my notes. I have what we've already talked about, but maybe in a more condensed form, so it's not so spread out all over the place. So again, if z is a function of x and y, then if you take the first derivative with respect to x, you're treating x as a variable, and you're treating y as a number or a constant. So here's some of the notations for it. And then if you take the first derivative with respect to y, you're treating y as a variable and x as a constant or a number. And here's some of the notations for that. And then for the second derivative, again, if z is a function of x and y, then if you're going to do xx, right, so this is the first one, xx, so with respect to x both times, x is a variable and y is a constant both times. And here's those notations, okay? If you're going to do it with respect to y both times, x is a constant both times, y is a variable both times. Here's those notations. But then if you're going to do x first, then y, then the first time, x is a variable, y is a constant. Second time, y is a constant, x is a variable. Here's some notations again. See the D's, they look backwards. They look backwards. So be careful. That's because if you did it with parentheses, it would look like, hold on, D, DF, which one was I doing? Let me look at my paper. X first and then Y. So it would be X, Y. So that's what it would look like if you, did it with the parentheses. This first and then this. And so that's why here it looks backwards. Okay, so think about it with the parentheses. It makes more sense. Okay, sorry, this is squished because I was trying to get it all on one paper. The second partial derivative, if you're going to do it with respect to y first and then x, the first time x is a constant, y is a variable. Second time x variable, y a constant. Here's the notations. Again, the d's look backwards. So I don't know. I do this sometimes. I don't know if I can get it good. I can't. I was going to try to get all the paper in one and focus it in case you want to like screenshot it and print it out. I do that sometimes, but I don't know if that's going to work really well. Anyway, I tried. Okay, let's look at some problems. So 1 to 22, you're finding the partial with respect to x and the partial with respect to y. So these are just the first derivatives. Okay, so for the first few to get you started, I reminded you which one's a variable and which one's a constant. They're nice. They take turns. They don't fight. Unlike my kids. Actually, my kids don't fight because they're 8 years apart and one of them lives in Arizona. So they don't fight anymore, but they used to. So not partial derivatives, though. They are very well behaved. They were raised very well. This is our function, number 2. Number 2 is a polynomial. Okay, so, sorry, I was trying to get my camera to focus. Partial with respect to x. X is a variable, y is a constant. So here, variable, take the derivative. Here, this is like a variable times a number. So the number just hangs out and waits patiently. You take the derivative of the variable, it's a 1. Okay, this is a number. The derivative of a number is 0. So it would be this. All right, so try the next one by yourself. The df dy. Try that by yourself. Pause the video. Try. By the way, hold on. Well, you might have already paused the video, but now you're back. Whatever. I don't know if you guys do this or not. I think I mentioned it in the first video. If you're not doing this, you need to start. You need to work the examples with me. If you're just watching the videos, you're not getting nearly as much out of it as you could. So don't just watch the videos. Work the problems with me. That's why they're videos. You can pause them. You can, if I'm going too fast, I'm talking too fast, I'm moving too fast, whatever, pause it. Try it by yourself as I go for every problem, not just the ones that I tell you to pause the video for. So when you finish watching the video, you should have on your paper worked out every single problem that I've worked because you're doing it along with me. Okay, that's kind of the whole point here. Okay, now, here's this one. So, my dog is whining. Hold on. Say hello. This is my dog. Her name's Aubie. Apparently she wants out. So I can't pause the video. So sorry. I have to be rude and get up and open the door. Okay, you like my blue chair? Okay, where was I? Here we go. Y is a variable. X is a constant. So going back up here, constant, derivative is 0. Number times a variable, so the number just hangs out. Derivative of the variable is a 1, and then variable, so take the derivative. So it'll be this. Okay. All right, let's try another one. This next one is chain rule. So here's my f. I wanna do one of them always and have you do the other one. So let me cover up some paper. I mean, get some paper to cover up this problem. Okay, so this is the partial with respect to x. So chain rule, bring the power down, don't mess with what's inside, subtract 1 from the power, then go back and take the derivative of what's inside. So if you're taking the derivative with respect to x, x is a variable, y is a number. So variable, derivative would be 2. Number, the derivative would be 0. So this 2 minus 0 is 2, 2 times 3 is 6, so it would be this. So you do by yourself df dy. So you'll have to pause the video, try that by yourself, and then check your answer. Now my dog is barking about something else. I'm not getting up again. She's just going to have to get over it because I can't pause this video. You guys can pause the video because you're watching it. I cannot pause the video when I'm making it. So I'm just going to ignore her. Okay, derivative with respect to y. Same thing on the outer. The outer derivative doesn't change. See, this outer derivative doesn't change? But the inner derivative of 2x, that's a number, 0. Derivative of negative 3y, that's a variable, negative 3. So 0 minus 3 is negative 3, times 3 is negative 9, so it'll be this. I think she's probably out of water. So she's probably going to bark the whole video. I hope you can't hear her because it's driving me crazy. Probably driving you crazy too if you can hear her. Let's try this one. This one is, for the x, going to be quotient rule. All right, so quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Multiply here. Get this. X squared minus 2x negative. X squared minus 2x squared. That finally got it right. There we go. Is negative x squared. Okay, so it'd be this. But for the y, notice on the y, the derivative is still quotient rule, but notice on the top the derivative is 0 because x is a number now with respect to y. So that whole piece goes away because the derivative is 0. Okay. And so then now the top times the derivative of the bottom over the bottom squared. So it'd just be this. Okay. All right, let's try some more. So here we have tangent inverse of y over x. So here, just as a note, sometimes it's easier to break these up. It's multiplication, so you can't totally separate them, but you can look at them separately. You've got y, and you've got 1 over x. All right, so let's try the first one. So tangent inverse, the derivative of tangent inverse, hold on, let me write it right here. Tangent inverse of x, I'm going to have to kill my dog, is this. Okay, that's what it is in general, but now we have something different in place of the x, so we're going to have to put something different in place of the x, but that's the formula. Okay, so we have what was in here, we put that in place of the x, but then by chain rule, we have to take the derivative of that. So to take the derivative of that, since it's with respect to x, looking at it right here, the y is a constant, so it just hangs out, and then I'm taking the derivative of 1 over x, which is negative 1 over x squared. And then I'm going to clean this up a little bit, so the negative I put in the top with the y, the x squared I put in the bottom, and then when you distribute it, see how here when you distribute it, the x squareds cancel, and so it simplifies to this. You don't want to leave complex fractions, so you should never leave a complex fraction in your answer, so you want to fix that. All right, so you try df dy by yourself. Pause the video, try it by yourself. All right, hopefully you're actually trying these by yourself. If you're not, you're robbing yourself of a very valuable learning opportunity because this is extremely important. Partial derivatives are something you've got to know how to do for the whole rest of the semester. And if you can't do it, you're not going to do well. And so really important that you get a good foundation on this. So practice, 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 practice. Okay. All right, here's the, with respect to y. So same thing for the tangent inverse. This is the same. But for my inner derivative, the derivative of y is 1. This is a constant, so it just hangs out. So it's this. Now when I distribute it, see how this was an x squared and this was an x, so it didn't totally cancel. That's a complex fraction, which is not a good thing. Complex fractions are fractions that have a fraction in either their numerator or their denominator, and you don't want to leave that. That would not be simplified completely if you left that. So to fix it, I multiplied by x over x to make it where it's not a complex fraction anymore, and I ended up with this. All right, I hope this is making sense. Let's look at some from the next group of problems. Anybody want a dog? I have one you can have for free. If you want her, you can have her. She drives me crazy. Okay, here, can you hear that? She's just barking like crazy. Here, I have a function of 3 variables. So same idea, taking the first derivatives, but I have a function of 3 variables, so it's 3 derivatives that I have to take. Okay, so here's this one. Now, because this is our first one of these, I wrote the words. So for f sub x is a variable, y and z are numbers. So you've got variable, number, 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 variable, number. I think somebody in my family just got home and gave her some more water. Hooray. Thank you, Lord. I do not have to listen to that stupid dog anymore. God is good. Okay, so here's my derivative with respect to x. Derivative of x is 1, y is a number. These are both numbers, so the derivative is 0. This is 1, and that's a number, so it'd be this. So it's just y plus z. So you try the next two by yourself. Okay, try f sub y and f sub z. All right, are you ready? F sub y is a variable, x and z are constants. So this is a number. Thank you for giving her water. Yeah. Number times a variable, variable times a number, number, number. So you have derivative of y is 1. These were both numbers, so it's just 0. So x plus z. And then for f of z, is a variable. The other two are numbers. So you have x plus y. All right, let's try another one of those. number 30. Okay, number 30. So we'll do x together and you try y and z by yourself. So here's x. For x, both of these are numbers, so they just hang out in front and you ignore them. And then here's my variable in here. So for a natural log, the derivative of a natural log, it's 1 over the thing you're taking the log of, and then times the derivative of the thing you're taking the log of. Okay, so the x is a variable, y is a constant, so it would be this. And then notice those y's will cancel. Well, I didn't cancel them yet. Here they are. Then they cancel the y's, and so you end up with this. All right, so before you try it by yourself, notice for the y, because there's a y here and a y here, you're going to have to do product rule. But for the z, since there's just a z here, you don't. Okay, so try y and z by yourself, pause the video, and then come back. All right, so f sub y needs product rule. So I have this piece and this piece. That's my two pieces for product rule. So here would be the derivative of yz times the other piece, and then plus yz times the derivative of this piece. Clean it up a little bit. X's and y's cancel. So you have this. And then for the z, this whole piece is just a number, and so you don't have to do anything with it. It's just the z you're taking the derivative of, so it'd just be this. All right, so let's look at the next set of problems. 41 to 50, it says find all the second order partial derivatives. So second derivatives here. So there's 2 first derivatives and 4 second derivatives. So you're going to have 6 total. And our first one, I won't use focus. Focus. Okay, our first one is this. So we take our 2 first partial derivatives. And so I put a little dot here by them so you can see them. So here's my partial with respect to x. It's chain rule again. Outer derivative is cosine. Inner derivative is this. Same thing for the y. Outer derivative cosine. Inner derivative is this. So those are my 2 partial derivatives of my first one. So now for my second one, I wrote both notations so you could see. So I'm going back up here, taking the derivative with respect to x. So y is just a number. It just hangs out front. Derivative of cosine, negative sine, and then the derivative of what's inside. That was chain rule again. And then I can put these y's together and write it this way. Okay. Now for the y, I go back up here to the y. X is just a number, so I put it up front and ignore it. Derivative of cosine, negative sine. Inner derivative is this, so it simplifies to this. All right, and then f sub xy. Notice again the backwardsness of the curly d notations. Compare these two. Okay, so this is the derivative of. It's the derivative of the derivative. This is the second derivative. So it's the derivative of this, but you're doing it with respect to y. So you're taking the derivative with respect to y of this, which was the derivative with respect to x. Okay, so here's the derivative with respect to x. I'm taking the derivative with respect to y. There's a y here and a y here, so it needs product rule. Okay, so for product rule, derivative of y is 1 times the cosine, then plus y, and the derivative of the cosine, outer derivative, inner derivative, clean it up. Now, as I told you, pretty much always, and I think always in this book, f sub y x is the same thing, but you can use it as a way to test and make sure you have done it correctly. If you'll go ahead and actually compute f sub y x, then if you don't get the same thing, you know you made an error somewhere and you can go back and find it, because you might have made an error up here in your first derivatives and you can catch it down here with your second derivative. So do the work even though you know you should get the same answer. All right, so y sub x, again, here's the 2 different notations. This one seems backwards, but this is what's going on. So you're taking the derivative of f sub y with respect to x. So here was the derivative with respect to y. And I'm taking the derivative with respect to x. Here's the x, here's the x, requires product rule. So it simplifies down to this, which, as you can see, same thing. So I feel pretty confident that we did that right. All right, next. I got pages everywhere. Hold on. Try to put my pages back in the right order. Sorry. And that's probably awkward for you to watch. Okay. This is a long video. Okay, here is 48, same thing. So if you want to try this whole thing by yourself, you can pause the video, try the whole thing by yourself. You should have, again, 2 first derivatives and 4 second derivatives. So I'm just going to, hopefully you pause the video. And then I'm just going to show this to you all at once so you can check your answers, and I'll talk you through in case you miss any of it. So here are my first derivatives. So partial with respect to x, the y is a constant, it just hangs out. For the e, you bring the e down, don't change it, and then you multiply by the derivative of the power. so it simplifies to this. And then for the y, you've got a y here and a y here, so you need a product rule. Okay, so here's the first piece, here's the second piece, clean it up. And you don't have to do this, but I just factored out the e. You don't have to do that. So if you didn't factor out the e, that's okay. So here's my two first partial derivatives, and again, it could look like this if you want to, that's fine. All right, partial with respect to x. Again, go back up here, take the partial with respect to x, and x here, I have to do product rule. So I have this piece and this piece, simplifies down to this, or if you want to, you don't have to, but you can factor out a 2y and the e, and it would be this. Okay, derivative with respect to y, again, go back up here or here, and take the derivative with respect to y. It needs product rule. And so here's my two pieces for product rule. Clean it up a little bit, it simplifies to this, or if you factor out the e, it looks like this. And then xy, taking the derivative with respect to y of what you got when you took the derivative with respect to x. So it's the derivative of this. Again, product rule. So again, simplifies to this, or if you factor it out, this. And then to double check yourself and make sure you did it right, let's go ahead and compute this one. So the derivative with respect to x of this answer up here that I got when I took the derivative with respect to y. And that requires, it does not require product rule because there's no x here. So no x here, so it does not require product rule. And so this piece is just a number and it's just hanging out while I take the derivative of this piece. So it simplifies down to this. And so notice if you had not factored out your 2x e to the x squared minus y, then they wouldn't have looked the same. But they are the same because you can see if I factored out they're the same. So sometimes they may not look exactly equivalent because here I didn't factor out and here I did, but they're the same. All right, so let's do the same thing. Wait, hold on. What is different about these? Oh, here you're just, sorry, this is 51 to 54. All you're doing is the x, y, y, x piece, and you're showing they're the same. So you don't have to do the xx or the yy piece. All right, so you do still need the first derivatives. So I have to do both of the first derivatives. So here's both of my first derivatives with respect to x, with respect to y. I didn't put little dots by them, but here's my two first derivatives. And then now I'm taking, again, just the mixed ones, the x, y, y, x. And I want to show that they're the same thing. Okay, so I'm taking, this is the derivative with respect to x. I'm taking the derivative of that with respect to y. And then here's the derivative with respect to y. I'm taking that with respect to x. And so after simplification, they end up being the same thing, which they were supposed to. So you kind of already knew what was supposed to happen. All right, let's try something else now. 62. 62, it says, let f of xy equals x squared plus y cubed. Find the slope of the line tangent to the surface at the point and lying in, and it has two different planes. Okay, so here's my function. Here's my point. If you're in the plane -1, well, I didn't actually show it. Let me show it over here. Hold on. Give me just a second. So f of x, y equals, what was it? X squared plus y cubed. So if you're doing x equals -1, just so you can see why this works this way, you're replacing all of your x's with a -1. And then now this is what you're taking the derivative of. So if you take the derivative of this with respect to y, then see how that's just a constant? And so it's just 0. Okay, so that's why you get a 0 here, was because your x is a number, so the derivative of a number is a constant. And so this would be your derivative with respect to y. Now you plug in this point, so you plug in the 1 for the y, and that would be the slope, 3. So let's try it for x. If you're in the plane y equals 1, so again I can show you over here, if y equals 1, it's f of x 1, which would be x squared plus 1 cubed, which is x squared plus 1. So the derivative of that, because that's a constant, is just 0. So that's why you get a 0 here. And so you get 2x, and then you're plugging in the point, and so you get -2 okay, for the slope. All right, so let's look at an implicit differentiation one. 66. Is that 66? Yes. Okay. It says find the value of dx dz. So notice here you're taking the derivative of x with respect to z. And so x is the function, well, let me write it right here. So what you have now is you have x equals a function of yz. So they're switching it up on you. Normally it's z equals xy, but now it's x is a function of y and z. So this is an implicit differentiation problem. And every time, because x is a function. So every time you take a derivative of an x, you've got to put a dx dz or a dx dy on the end of it because x is a function of y and z. All right, so I wrote that up here. So here's my equation. Notice it's not solved for x, and so that's why it requires implicit differentiation. Implicit differentiation is what you do when it's not solved for the variable that you want. So it's not solved for x. So x is a function of y and z. So x is a function. Wait, what did they? Oh, okay. I didn't read that part. This is all they want. So if they want the derivative of x with respect to z, then that's why z was the variable and y was the constant. I thought I had to do both. I thought I had to do dx dz and dx dy, but no, just dx dz. So this is the only one I have to do. So x is a function, z is a variable, y is a constant. All right, so here, function times variable. Function times variable needs product rule. So when you take the derivative of x, it's 1, but because x is a function, it needs a dx dz on the end, and then times x for the product rule part. And then now bring the x down for the product rule part. Z is just a variable, so the derivative of z is 1. All right, y is a number, so it just comes down here. X is a function, so I take the derivative like normal, which is 1 over x, but then because it was a function, I have to stick a dx dz on the end. And then again, here's another x. It's a function, so stick a dx dz on the end. 4 is a number, so that's just 0. And then your goal is to solve for dx dz. So first I just kind of, dropped these parentheses, cleaned it up a little bit. And then grouping, if it has a dx dz, put it on the left. If not, put it on the right. Factor out the dx dz. Divide by the stuff in parentheses to get this, and then now you're plugging in the point. So here was my point, and I plug it in, and it simplifies down to 1/6. So that is implicit differentiation. We're going to look at more implicit differentiation later, but on implicit differentiation, when you have a function of 2 variables, so you have 3 variables total, but a function of 2 variables. One of them's a function, one of them's a variable, and one of them's a constant. So the one on top is the function, the one on bottom is the variable, and then the one that's not included, that's the constant. Okay, so we're going to look at more, like I said, in another section. But for now, hopefully that's enough for you to be able to do your homework. So if you have any questions, just send me an email.